Welcome to this lecture series in linear algebra. In this lecture, we'll look at the very important notion of a basis, and two of the main things that we need to follow this lecture is the notion of span of a list of vectors or a set of vectors. So if we have a set A of vectors in a vector space V, then span A, we define this as the intersection of all the subspaces that contain A. And this we also saw it can be written as, or can be expressed as, the set of all the linear combinations that one can form using finitely many elements of A. So this is something that we will need, and we need the notion of finitely generated vector space. So a finitely generated vector space is a vector space for which one can find a finite subset of vectors, meaning V is said to be finitely generated if there is a finite subset A of V whose span is the entire space V. Right. And most examples of vector spaces that we saw are all finitely generated. For instance, this is finitely generated, this is finitely generated, and this is also finitely generated as long as X is finite, but perhaps we haven't proved it. This will be an exercise at some point. Okay. Here are some problems for practice. And now let us get started. So what is a basis? First, we will define what is a spanning list, and then we will define a basis. So fix a vector space V, the base field being F, and suppose we are given some n vectors from the vector space V. We say that this list is a spanning list if this is a spanning set, which is same as saying if you take the span of these vectors, you get the entire vector space. So I just wanted to spell it out. Of course, there is only one possible interpretation that one would come up with if I had used this phrase without defining it, but I just wanted to leave no room for confusion. So we will use the notion of a spanning set and the notion of a spanning list, but they are only superficially different. All right, and now we can define what is a basis. So we say that this list of vectors is a basis if two things happen. If it is a spanning list, first of all, if it is a linearly independent spanning list, basically, if it is a linearly independent spanning list. So we say this list is a basis if, first of all, it is a linearly independent list, meaning the only linear combination of them that vanishes is the trivial linear combination, meaning the only scalars that you can choose to make it vanish are the scalars 0, 0, 0, 0 everywhere, and that it is a spanning list, which we just defined. All of these vectors together should span the entire vector space. So that is the notion of a basis. The way I have defined a basis, it is a list. There is a reason why we are using list. In some books, you may see a set of vectors to be a basis. Again, the difference is somewhat superficial, but it will be convenient for us to make it a list, an ordered thing rather than an unordered thing. It's just when we will look at linear transformations and matrices of linear transformations, the ordering of the basis will matter, and therefore it is good to define a basis as an ordered thing rather than an unordered thing. Okay, so let's see some examples of bases. So we will look at the standard basis. Yeah, so let F be a field and n be a positive integer. Let V be this vector space, which is to say that V is actually this quadruple, just to spell it out, where we know what is the definition of plus and what is the definition of dot. So this is we looked at this example way earlier. By that I mean in the second lecture. All right, so this space is our vector space, and now we will write down a basis for it. So let E1 be this, E2 be that thing, and so on. And we have looked at these vectors earlier. These are just some vectors from Fn. And I think we have previously commented that the span of these vectors is everything. That's absolutely trivial. So if you don't immediately see it, you should spend time on it. So that is there, and now they are also linearly independent. So why they are linearly independent, that's also trivial. So if some linear combination of these vectors vanishes, then this particular vector is 0. Why? Because this vector is same as that vector. If you just use the definition of scaling and addition, you get this is 0, which is to say that each alpha I is 0. So the only way a linear combination vanishes is when each scalar is 0, and hence these vectors are linearly independent. The upshot is that, or you can summarize what we just did by saying that this guy, E1 up to En, is a basis of Fn. And this is called the standard basis of Fn. Okay, so just one example. We will perhaps look at other examples in exercises or in due course. All right. So here is a very important property of a basis. So suppose this is a basis of a vector space V and where the base field is F. Then for any vector V, there is a unique list of vectors alpha 1 up to alpha n, unique list of scalars alpha 1 up to alpha n, such that the corresponding linear combination is the vector V. So the important point here, or the crucial point here, is the uniqueness of these scalars. Since this is a basis, in particular, this is a spanning list. And since this is a spanning list, for any vector V, there obviously exist such scalars so that the corresponding linear combination is V. That's what it means for a list to be a spanning list. The point is that this is a unique list. There is only one list of scalars which yields a given vector. You will not find two different alpha 1 up to alpha n such that the linear combination is again V. So it is a very simple property, just a matter of unraveling the definitions, but it is important to realize this fact. Let's prove this. So existence is clear, and we will not spend any time on existence. Let me just directly prove uniqueness. What do we need to prove uniqueness? So say alpha 1 up to alpha n and beta 1 up to beta n are such that the corresponding linear combination is the vector V in both cases. So I should start the proof with fix a vector V in the vector space and then proceed. So such that the corresponding linear combinations are both V. Okay, what do we want to do? We want to show that. That's what it means to show uniqueness. Okay. So it's very simple. Let me use succinct notation to express these things just for brevity. Oops. Okay. So we have this thing minus this thing is v minus v, which is 0. Okay, great. But what is the left-hand side? The left-hand side is also that, and hence this is 0. So these are some scalars such that the corresponding linear combinations of the combination of the VI's is 0. So therefore each of these scalars must be 0. Why? Because our list is a linearly independent list. Right? A basis is in particular a linearly independent list, and hence the only way you can get a linear combination to yield 0 is that each scalar participating in the linear combination is 0. Therefore, alpha I minus beta I is 0 for all I, and therefore we are done. That's it. That's what we wanted to show. It's a very simple proof, straightforward, follow your nose argument, but I did it in full detail because we are only at the beginning of this course. It is good to see proofs in full details, and generally my idea is to present proofs in full details. Yeah. Okay. Now for the most important thing. Every finitely generated vector space has a basis. Right? So the notion of we for this space f to the n, we explicitly were able to write down a basis, but that was the existence of a basis for f to the n was just a consequence of the fact that f to the n is finitely generated. All right. So this is not what we are going to do, and I think this will be the last thing that we will do. Yeah, this is the last thing for this lecture. Okay. So here is the proof. And this style of the proof is rampant throughout all mathematics. We know that, so fix a finitely generated vector space. So let V be a finitely generated vector space. And say F is the base field. Okay. We want to show that V has a basis. Let me not write that. So, since it is a finitely generated vector space, there is a finite spanning list, or let me say there is a finite spanning set, and hence we can find n vectors such that the corresponding list is a spanning list. Right? So what we will do is that we will pick a spanning list of smallest possible size. There is a spanning list of size something, some n, some finite n, could be million, could be whatever. Amongst all the finite spanning lists, choose one of the smallest possible size. There could be multiple such lists. There could be multiple lists with the smallest size, all of which span the vector space. Just pick one amongst those. Okay? So here is what we want to write. So let, and this is the key, basically this is the proof, let v1 up to vn be a spanning list of smallest possible size. And you should look at the well ordering principle if there is any confusion about this. There are a series of lectures on the well ordering principle in my playlist named Kickstart. So that is what we are really invoking here. If you want to be really, really formal about this step, what we are invoking is the well ordering principle, but this is really a matter of common sense. So I do not want to write down the gory details just to satisfy the rigor. Okay, so we have picked a spanning list of smallest possible size. We will show that this is a basis. and that will finish the proof. Okay, so this is already a spanning list. To show that this is a basis, all we now need to do is that this is a linearly independent list. So we will proceed by contradiction. So assume on the contrary that this is linearly dependent, and therefore we can find scalars alpha 1 up to alpha n such that the corresponding linear combination vanishes. Okay, let us call this equation as star, and here I also need to write that not all of the alpha i's are 0. Or let me say at least one is non-zero. So once again, since we assumed that this is linearly dependent, there is a non-trivial linear combination which vanishes, which is to say that there exists alpha 1 up to alpha n, at least one of which is non-zero, such that the corresponding linear combination is 0. So that is fine. And without loss of generality, we may assume that it is actually alpha n that is non-zero. So you may just relabel the things so that the nth person here is non-zero. So that's not cheating. Okay, so what we get is from star we have alpha 1 upon minus alpha 1 upon alpha n v1 minus alpha 2 upon alpha n v2. This is equal to Vn. All we did was just some algebra. We took this to the right hand side and divided both sides by minus alpha n to get this equation. Okay. So here is our claim. This is a spanning list. Okay. So once we show this will finish the proof, because then we would have produced a spanning list of size smaller than the size of this guy, but this was chosen to be the spanning list of smallest possible size. So as soon as we prove this claim, we will have reached a contradiction, and hence the proof will be finished. So this is now our final goal. So how do we prove this? Okay, so suppose this is so we want to show this is a spanning list. So what do we do? So pick some vector arbitrarily, and we will show that it is in the span of this list, and hence we will be done. So first of all, since this is a spanning list, there is some list of scalars beta 1 up to beta n such that the corresponding linear combination is V. Okay. This is just using the fact that this is a spanning list. And now we just substitute the expression of Vn that we have here. Just substitute the expression of Vn here. So let's call this double star. Use double star basically. So if we use double star, I do not want to use a different page, so let's just try to finish it here. So by double star, we have this plus the expression for Vn. This is equal to V, but what is the expression for Vn? Minus alpha 1 by alpha n V1 minus dot 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 that. Right? And now we just collect the coefficients. So we will collect the coefficients for v1, for v2, and vn minus 1, and that will, I mean, even from here you can see that v is actually in the span of v1 up to vn minus 1, but let's write it down. So from the last equation, what we see is beta 1 beta 1 minus alpha 1 by alpha n times v1 plus dot 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 this is equal to v, which implies if we call this as gamma 1 up to this as gamma n minus 1, these are all scalars, so we get gamma 1 v1 plus dot 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 gamma n minus 1 vn minus 1 is v, which is to say v lies in span of that, and since v was arbitrary, this proves the claim and hence brings us to the required contradiction, and we are done. Okay, so every finitely generated vector space has a basis, which has a very nice proof, very simple proof, but very nice proof. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.